Yeah, we can start now.
Thank you, sir. Good evening, everyone. I am Arunkumar Heddallikar. So I am going to present paper titled as Ground-Based ArcSAR Interferometry using VNA. So author's affiliations are given below. So the main aim and objective of this research work is that to prepare a portable compact ArcSAR system using VNA. After preparing this hardware, so we have to do the field campaign of ArcSAR, that is experimentation, image generation, and its validation. After that, we will do the as an interferometry field demonstration. So this is the experiment test setup. So we can see in this image is the rotating table, which rotates 360-degree in angular motions. So we have two horn antennas, that is bistatic configuration. So we are using VNA. In this image, we can see this is a vector network analyzer. Here, this is used for SFCW radar, stepped frequency continuous wave radar. So we have connected this VNA using coaxial cable to the antenna in bistatic configuration. So we have computer to control this rotating table, and VNA will radiate and receive the backscattered signal. So this is a little different. When we see the SAR means that is a linear motion, which is side looking. This is a ArcSAR, which is angularly rotating and acquiring the backscattered data, and it will process and make the images. So for to create a better resolution image, this angular resolution mainly depends on this called boom length. So what happens is in this image we see when this boom length is more, we will get the better angular resolution SAR images, which is defined by these equations. For this experiment, so these are the specifications we have selected. It operates in KU band and with 2 GHz bandwidth, and antenna beam width 30° by 10°, which is having 20 dBi gain, and boom length is around 50 centimeter. So we are expecting resolutions of around 0.075 meter. So this VNA for this experiment is used, which gives dynamic range of 110 dB. So this is the test scenario. We have used point targets for imaging and validating the SAR image generated using this setup. So we have rotated this turntable up to 100°. So through that we are acquiring the backscattered signal. So these two point targets, we can see the backside that there is a wall which is around 6.5 meter away from the sensor. So these are the test setups specifications. So we are acquiring data at every 1 degree steps. So we are scanning up to 100° scan angle. Two targets, that is 25 centimeter point targets at a distance of 5.6 meter and 6 meter, which are kept, which is having a RCS of 7 dB square meters. So expected azimuth resolution in this case is 0.0467 radian. So once data are acquired and they are processed, so this is the processed SAR image. So in this, we have observed the range migrations. After doing RCMC, so we could able to focus these 2 point targets, which are separated in both range and in azimuth directions. Once these SAR images are acquired, so in the next set, we are comparing this one. We took 2 SAR data and we are seeing the coherence plot. In this clearly we can see this is the wall reflections, and these 2 are the point targets. Because they have good RCS, that's why we could able to see the better coherence for these areas. After these SAR image generations, so we have seen this impulse response. Because to validate any quality of SAR image, we have to see the azimuth impulse response of the SAR, so which is coming around 0.0467 radian. So measured and estimated both are almost matching. So this shows this the quality of the test setup prepared. After that, we took this one to the field campaign. On that, in our office, we have terrace. We have placed this ArcSAR setup because this is a compact and portable. We can place anywhere and do the experimentation. So in this right hand side, we can see this image. This is a IIT campus image. So this is, we can see the overhead water tank, and this is a residential building, Ananta building. So we could able to see the in the SAR ArcSAR image clearly. This is the these backscattered from the water tank, and this is from the residential building. So like this, we can clearly correlate the experimentation and this through Google Earth image. So now we have to demonstrate for the displacement, that is interferometric the configuration. So for this, we used screw gauge arrangement. So with this screw gauge, we can push the corner reflector in the radar directions. That is controlled displacement creation. So this setup will create an displacement up to 0.01 millimeter, and maximum it can go for 20 millimeter. So one point target we are pushing using this screw gauge arrangement. Other corner reflector we are keeping as it is. So we can see this the corner reflector which is mounted on the tripod, which is the displayed. In the displacement map, we can clearly see that the displacement in the corner reflector, it's clearly visible. Whereas right side corner reflector, there is no displacement because we are not disturbing those that corner reflectors. When we see the time series plots, so there is some disturbance we can see in that. Because to conduct this entire experiment, it took 6 hours. During that period, so we have observed a lot of wind to conduct this experiment. That's why the disturbance we can see in the time series plot. So with this displacement and time series plot, we can conclude that we using VNA-based instrument, we can conduct a portable, compact IRCSAR interferometry experiments. So I conclude this one. So we prepared this portable, compact IRCSAR system using VNA, and we have generated SAR images of point targets, and we have validated with by seeing the azimuth impulse response. And we successfully conducted the field campaign of IRCSAR experiment, and even we did the interferometric experiments too. So I have used the references. This is.
Yeah, let us
Thank you.
So, very good.
Yes, sir, please.
You have used for single receiver or two receiver?
Here, sir, single receiver. So in this, we are using bistatic. One is as a transmitting, other is a receiving.
These bistatic mode we are.
This is bistatic mode.
Any other question?
Sir, now your interferometric plot, can you just?
Yes, sir.
Is the backscattering only, not a bistatic. They are almost located in co-located.
This one, sir,
Yeah.
displacement.
Here, for this, like, can you just show, find out your two targets?
Yes, sir. See, this, sir, this is the point target, 25 centimeter, which is mounted on the tripod.
Which is displaced.
This is displaced. That is with controlled experiment. And this, which is mounted on that wooden block. So this we can see there is no displacement in this one.
But as per your color bar,
Correct.
it shows some color indication. As such, it shows around 2-3 mm difference which is coming.
This one, sir.
Yeah.
This is almost, sir. You see, this is a dark this one, no, 0 to 1. So the scale is wider, so I cannot.
So what can be the minimum resolution that you can detect it on?
Actually, so using
You moved by about what? You moved by about?
this is I moved by 0.5 mm steps. So with this SFCW with VNA instrument, we have a capability of we can measure 1 micrometer. Tomorrow I am having same on that same thing. That is little different one. So up to that much we have the capability to measure the change in the target displacement.
There is one.
Yes, sir.
Quick question is
This one.
Shape of the tank, you know.
Thanks, yes, sir.
Bunch of distortion. How do you compensate for that?
This one you were saying, sir.
Yeah. Yeah.
Actually, sir, when your radar it looks it is receiving the backscatter from this that surface which is at the towards the radar direction. So it is coming like this. And because I'm using 2 GHz bandwidth, that's why we can see the spread in the range. Because the tank is quite height it is there, and I'm having the angle also 10-degree angle. With that, it is looking like spread in the range direction.
Okay.
you implemented the synthetic aperture concept.
Yes, sir. This is the angular one, sir.
Okay, so what is the synthetic aperture length in the angular direction?
Here, sir, synthetic aperture length is,
0.047 is the synthetic aperture length in the angular direction.
no, here I have to move, sir, up to the beam width of the antenna. That is 30 degree. In my azimuth direction, I am having 30 degrees my beam width.
Okay.
In the stable. So I have to, in the specification, azimuth beam width is 30 degree. So I have to scan up to 30 degree. When we go for a linear strip map mode, there also we have to do the complete scanning of
Over the synthetic aperture.
synthetic aperture. That is antenna beam width.
Thank you. So the next talk is the title of the paper is Dead Range Gap Estimation in NISAR and SAR, and it will be presented by Samneet Thakur.
Yes. Afternoon. My name is Samneet Thakur, and the co-authors for this paper are K.M. Agrawal and V. Manavala Ramanujam. The title of the paper is Dead Range Gaps Estimation in NISAR S-band SAR. So these are the contents of the presentation. First, I will be talking about a bit about NISAR, and then the concept of staggered PRI in NISAR, then the consequences of staggered PRI SAR and dead range gaps, then dead range gaps estimation methods, then the simulation strategy for one-dimensional point targets, results of those simulation strategy of the estimation methods, then simulation strategy for distributed targets and the results on the same, and finally the conclusion and references. So NISAR is it stands for NASA ISRO Synthetic Aperture Radar. It is world's first dual frequency sweep SAR that L band is operating at nominal center frequency of 1.2575 gigahertz. S band is operating at 3.2 gigahertz. L band instrument is developed by NASA, and S band instrument is developed by ISRO. It comes under the category of high resolution wide swath mission. It will provide 6 meter data at 6 meter azimuth resolution and at 240 kilometer swath with 12-day repeativity coverage. So it is using sweep SAR concept to generate this kind of data. So for example, on the left hand side, you can see these, there are like this is what we call as primary feed. We have like 12 primary trans-receive integrated modules for L band and 24 for S band. During transmit event, all of these TR modules will be activated, and they will form a small aperture on this secondary reflector antenna, which will form a large footprint on the ground, imaging full to 40 kilometer swath. While during the receive event, each of the subswath, using the sweep SAR concept, the reflected echoes from each of the subswath will be routed to corresponding trim, and these like receive beams will be added coherently using digital beam forming process, and full to 40 kilometer swath data will be generated. So in order to cover 240 kilometer swath, we need 1200 microsecond data window, and for NISAR, our PRI, that is pulse repetition interval, depending upon modes, it is going from 400 microsecond to 600 microsecond. So what is happening here is that while you are receiving the data, this total data window is 1200 microsecond, and these PRIs values are roughly in the order of 400-500 microsecond. So during this transmit event, we have to switch off the receive. So we have to switch off the receiver. So we will not be receiving any data. So these are basically what we are calling as dead range gaps. So depending upon the the slant ranges of interest, there can be 2, 3, or 4 such type of events in a given receive data window. And if your PRI is constant, for example, all of these values are constant, the location of these dead range gaps will remain same across all azimuth records. So what will happen, the wide 240-kilometer swath data will be divided into smaller multiple subswaths separated by these pulse width equivalent dead range gaps. So in order to do away with that, we are staggering the PRI. That is, we are varying the PRI from one azimuth record to next. And what that process is doing, basically, it is distributing these dead range gaps across SAR. So as you can see, for example, here there is no adjacent missing samples across the azimuth. So now what happens because of these dead range gaps is that, for example, I have shown here the simulation one. On the right hand side, you can see it is standard point target response. And if you don't estimate these dead range gaps, or we call missing samples in signal processing term, it will make the data locally undersample, and it will alias the data spectrum, and it will generate the ambiguities or the ghost targets, as we call them. For example, the peak ambiguity, as we can see here, is up to -30 dB level with respect to peak value. So it degrades the ISLR of the point target, and it reduces the contrast of the processed image. It is very much visible in the low SNR regions, for example, lakes, oceans, etc. Hence, the underline is that we have to estimate missing samples. So there are two types of estimation methods that has been studied in earlier studies. One is BLU, that stands for Best Linear Unbiased Estimator. It is time domain based approach. And the second one is MIA, Missing Data Based Iterative Adaptive Approach. It is spectrum domain based approach. So now during the simulation of 1D point targets, initially we simulated a staggered PRI sequence, and then we generated a chub at those staggered PRI values, and then blind range gaps were generated, and some samples were assigned zeros as per these blind ranges in azimuth signal. And then we applied estimation methods, whether we have to estimate the data or not using these two previous methods. And then we resampled the data to uniform space because data is not uniformly sampled. And then we compressed the data using azimuth replica, and then further point target analysis were performed. And during this process, we have also added additive white Gaussian noise to add the noise in the incoming data. So these are these are the simulation parameters that I have shown for one of the S-band standalone modes. So these are the results. It is the reference point target data where no missing data is there, and it is simply compressed. So these are our reference values, PSLR, ISLR, and resolution is 6 meter because we have it is around 6 meter because we have 12 meter secondary reflector antenna for NISAR. And when you do not estimate missing samples, as you can see, ISLR has degraded, and these are ghost targets or ambiguities that are appearing. But when you estimate these missing samples using BLU and MIA, our results are comparable to the reference one. The comparative analysis of different estimators are here. You can see that PSLR has improved, and the ISLR is significantly improved as compared to PSLR, and the resolution and the peak ambiguity levels are also has improved by almost 13 to 14 dB. So for this simulation, percentage of missing data were around 9.8 and SNR of 15 dB. So this is the response of these point targets for different SNR values. As you can see that with the increasing SNR, the ISLR and PSLR and the NMSE, that is normalized mean squared error, improves with increasing SNR for each type of estimators. Now moving to the distributed targets, we took this EOS04 data, and then we assigned some dead range gaps in it. You can see these dark range lines, and then then these were estimated either using BLU or using MIA, and then using conventional frequency domain algorithms like RDA, data was focused. So yeah, these on the right side I have shown the dead range gaps, the distribution across the swath, and these are the parameters. This is US04 data looking at C-band PRF is 3700 Hertz. And so on an average, 6.4% of data was missing in the whole scene. So these are like the estimation results. So it is reference image. It has no like missing data in it. So and on the right hand side, when the missing data was present, as you can see that these like very bright, what we call as ambiguities of ghost targets. These are basically the bleeding of energy of the coastal targets into lake or oceans. These have appeared, and what these have done is these have increased the mean and SD levels of these areas. So that is, and it has also reduced the contrast of the image. And if you estimate the using BLU and MIA, BLU is working better as compared to when you were not estimating the data, but its performance, at least for point targets, is not that good as compared to MIA. It is like significantly 1.5 dB away from MIA. So, but overall for other distributed targets, if you see over here, BLU works as compared to MIA, it works good also. And these are the times that it is taking to estimate the data. For example, it is taking 4 seconds using BLU and 180 seconds using MIA. So yeah, and yeah, it is for 11K range samples and 13K azimuth pulses, these timing that I'm showing here. So in the conclusion, the estimation of dead range gaps is a requirement. For point targets, MIA works well. It significantly suppresses the ambiguities. For the performance of all estimators improves with SNR, high SNRs. BLU, a time domain approach, is fast. MIA being a spectrum domain based iterative procedure is computationally exhaustive. It takes around 50 times more time as compared to BLU. For NISAR, because it will its data would be 50 times more than that of this scene here. So it will take around 3.5 minutes to estimate dead range gaps in NISAR scene using BLU, but 2.5 hours using MIA. So it makes practically impossible to use MIA for NISAR. So that is the baseline that we have. We will be using BLU. So these are the references that we have used for this study.
Let us thank Samneet Thakur for his presentation. So any questions? Yeah. So in case of staggered PRM system, you said we miss the data points because of LIC.
Sir, our not for staggered, even if the it was constant PRI SAR, because this data window is at 1200 microsecond, right? And these PRI values are 400, 450, something like that. But if your PRI is constant for this azimuth pulse, and then for the next also, these locations will remain same. For example, this blue color would be present here only. So your 240 kilometer swath will be subdivided into these small dead range gaps. So there is no use to then in that case to use like 240 kilometers.
Sample data very high. Suppose PRI is 100 and 200 kilowatts, and I sample like say.
But sir, in that case, then your PRF will become smaller, and then your data will become alias in azimuth direction.
But I will not miss any data points if I sample at a very high rate, like 10 times the PRF, 5 times the PRF.
That is okay, but that will degrade SNR part also. Like that issues will come out. Noise equivalent sigma naught values will also decrease because those are also functions of PRF.
Thank you. Nice presentation.
Good evening, everyone. I am presenting my topic surface displacement monitoring at Joshimath region, Uttarakhand, using SBAS-INSAR. So, This will be my table of content. I will be covering these topics. So next, for the motivation, as we can say, Northwest Himalayas are prone to disaster and developed as a hotspot for flood and landslide hazard due to the changing precipitation region. In the last year, 2023, we have a high precipitation anomaly in Himalayas. So we have seen several landslides events in Shimla and Manali side. And the whole Northwest Himalaya is prone to the disaster. There are several towns in the Himalayas that are at high risk due to the problem of ground subsidence and landslide. One of them is Joshimath. Second one we can take as the case of Shimla and Manali. So next, the non-invasive geospatial techniques hold the key to temporal monitoring of such unstable slopes in high altitude areas. Because the mountain valleys are very narrow, so we cannot measure deformation at every point with the common methods.
And that's in the deeper model show that that is the work on the influences of land use service on the landslide susceptibility region Kerala. Here we'll be going through the various stages of landslide susceptibility simulation and we'll be assessing the result that we have obtained from. So, coming to landslides. Landslides are basically this result from the downflow of rocks and other debris under influence of gravity. And this landslide susceptibility simulation takes into account the various condition factors that leads to the landslides and measures the probability of landslide occurring on the surface location. It is very integral to the implementation of early warning systems and serves as a model for sustainable land use organizing. Among the various conditioning factors, land use land cover is a very key factor as it influences the triggering of landslide by rain in a certain area. The first step in landslide susceptibility simulation is the construction of a spatial database. The database for the study region comprises of the various landslide conditioning factors and the landslide into the study region. Here we have considered 8 conditioning factors, community, elevation, slope, aspect. The land use and land cover for the years 2015 and 2023 derived from the answer 8 and 9 images for the respective years. The lithology data of the geological survey years of the data process. And the average monsoon rainfall was evaluated from the problem precipitation using the Google Earth. Landslide inventory, a total of 190 landslide events were identified from the beginning until 2023 from the various media platforms that have reported landslide events. Among the various condition factors, land use and land cover are quite important because it is something that varies over time and thus may be able to create variations in the landslide susceptibility of the region. And here we have used a landslide 8 and 9 images for estimating the land use and cover of the region for both 2015 and 2023, and we did that using ArcGIS Pro. This created classification models were evaluated using data functions, which is equal to the probability of correct classification. That is the probability of true positive to occur minus the probability of chance. That is the amount of agreement between the original data and the classified data for each of the various land use classes divided by 1 minus the probability of chance agreement. The calculated data function values for 2015 and 2023 were 0.88 and 0.94 respectively. Land use classification that we did for both years. And as you can see here, there is an increase in the amount of sparse vegetation and as well as the barren land over the 8 years that we have. And that suggests a decrease in the amount of dense vegetation over the years. And the next step after the construction of the spatial database is the modeling of landslide susceptibility for the study region. The PDT was done for both 2015 and 2023 with the ANTA project. It is an ensemble machine learning model which uses the concept of tag. So the idea behind tagging is to combine the results of different learning algorithms and aggregate all these results to create the final result of our model. Model was evaluated using ROCSC score and gave scores of 0.845 and 0.849 respectively for 2015 and 2022, suggesting that they are classified that can give good performance. The next step in the process is the creation of the susceptibility map, the access susceptibility map, which was done and the region was then classified based on its susceptibility into very low, low, moderate, high, and very high susceptibility classes. Landslide susceptibility maps for 2015 and 2022. So there is clearly an increase in the very high susceptibility class over the time period. And most of the landslide points are falling on this very high susceptibility region class, and some of them are falling the high susceptibility class. And go to the research section. Clearly, an increase in the amount of sparse vegetation, region, narrow land, and the power areas, and there is a decrease in the dense vegetation area also, as evident from the land use and power classification that we have obtained for the region. The percentage of area under the very high susceptibility zone increased from 7.68% to 15.24%, which is almost double the original value over the last 8 years. And there was also an increase in the very low susceptibility category over the time period that we chose. While there was a decrease in the low, moderate, and high susceptibility classes over the years, which suggests a conversion from all of these classes to the ones that have had an increase in their percentage of area. The analysis showed an increase in the built-up barren land and sparse vegetation, while the dense vegetation showed signs of reduction during the testing. And the landslide susceptibility of Uttarakhand also displayed changes with an increase in the areas falling under very high and very low susceptibility zones increasing with the under the very high susceptibility zone almost double the original value. And the reduction in the other three classes suggests a conversion into either of these classes that we have mentioned above. So the changes in landslide susceptibility and endurance of the years suggests the need to investigate any direct influence the data has on the fauna in more detail in the future, as it may provide the implementation of landslide early warning systems. Future explorations, the changes in landslide susceptibility and land use, land cover over the years suggests a relationship between these two. So we need to study any relationship that the land use, land cover has on the susceptibility of the region in more detail, as it may prove vital the deployment of the landslide early systems for the region. And the biases and uncertainties specific to data core contexts were identified by the region. And a long-standing tradition of systematic data recording in media is essential in eliminating these constraints. The organizers of the InGARSS 2023, on behalf of our lead, for giving us an opportunity to present our work here. Thank you and have a nice day.
Landslide is now. Landslide.
Landslide, yes, sir.
No. Resolution is very poor. We cannot detect many.
Actually,
30-meter landslide is hardly fine.
Yeah.
And the Sentinel 10-meter is better.
Kilometer is better, but I guess for 2015 I tried for Sentinel data, but I couldn't find at that time, so just went over the Landsat 8 and 9.
And list 3, list 4 is better.
That time nothing else needed for me. That's a Landsat.
Why you have chosen 2015?
So like the land use land cover changes will happen over a long period of time. So we decided to go for like an 8-year gap from 2023 to 2015, so that we can use like Landsat 8 and Landsat 9.
Why 2000? You said data is not available. 2000 a year, the data set is.
Yeah, Sentinel, I could have gone for like a later year, but there's an 8-year gap was what we had in mind regarding this thing. In the long of 8 years at least. Was 2015 was what I had in mind because I had Sentinel in mind at that time when I planned this work. So since the data was not available, I just switched to Landsat.
Did you go for any ground truth?
We actually used real data points. Like, we use Google Maps, and generate points from there, like real points of like vegetation, buildings like built up, battleland and all, and then compare that with the that we have. That's
Think you can try to compare your classification with the schematic layer.
Actually, there is a bias in the data because Lancer in my area had actually previously worked on the lenses of the Pluto Pidiki. And at that time, I used the data from that was available on Bhukosh. So it had around like 1,000+ data points for Lancer. But here in our case, we actually need the event, the date of the event when this event happened. So that data didn't have that.
No, in 2015, schematic.
It is confirmed that way. Because another thing is that our data is actually like low in number, like points, because of this time constant that we had. Otherwise, we could have done that. Proceeded.
Are you smoothing the filtering data? Are you smoothing filtering? You see, in classification, they smooth and filter it. Are you doing? Then small landslide will go away. See, otherwise you compare global map currently available from NISAR.
Yes, that's the thing. So, like, for the standard map, they will have taken some different inventory. So my inventory has this. The done data. So that's why I am planning to do the same thing, like collect more information on the Lancer events and like do better. That's all.
So this is the last presentation. So, okay. So, I don't. Okay, quickly. Some problem with doing this. Oh, okay. So, we can end up with thank you. Okay. The problem is that I'll say
So we'll conclude this session. Thank you to the chairs for conducting this session. And thank you to all the participants and presenters. See you tomorrow then.